Okay, so for number 1 and 2, you're just simply listing the first 5 terms. That should be very straightforward. Playing 1, 2, 3, 4, 5, work it out. Likely was number 2. So yeah, there's nothing more to it than number, that stuff. But for the next 8 questions, that's where we're probably doing a little bit of calculus, right? Some limits. We talked about a new rule called L'Hopital's rule. Um, Squeeze theorem could be another thing that we might need to consider. And I don't know what the heck just happened. How come I can't see? Okay, that is bizarre. That was so weird. Okay. Um, yeah. So for number 3, the way you could approach this analytically to find the limit of the sequence. So you want to know what the last term would be if the last term would converge. Not doing sums. We're doing that today. But we're just looking at what this last term potentially could be, or an infinite term could be. Would it converge? And for 3, it would. It would be -1/4. We know this with rational functions that, if you have like the degrees are the same for both top and bottom, so ratio of leading coefficients. So you could, we know that. But one way you could approach is if you take the limit as n approaches infinity, multiply top and bottom by 1/n² and do some reduction. And if you take each of those individual terms, which you're allowed to do for limit properties, like limit of 7/n as n approaches infinity is 0. The limit of 3/n² as n approaches infinity is 0, and so forth. You get -1/4. So you could do that. Another technique you could have done too, now that I've expanded your horizons with derivatives and this new rule called L'Hopital's rule. If you plug in infinity right now, what do you wind up getting? Basically, wind up getting infinity over negative infinity, right? And why is it negative infinity in the bottom, by the way? Yeah, it's a negative coefficient, right? We know that. But that's indeterminate. So what you could do is you could also take the derivative, right? If you take the derivative of this, what do you get? 2n-7. How about the other one? 10-8n. And here's the problem, is that if you still plug in infinity, are you still getting infinity of infinity? So what if you do a derivative again? What do you get now? Which is -1/4. So you have that luxury now. Now you know you could do this to find limits. You could do something called L'Hopital's rule. And I think we could apply that several times here. For number 4, but yeah, pretty good.
Like divide all the terms by like n
Yeah,
squared.
yeah, that's exactly what I did for number 3. Yeah, I did that. And you do likewise for number 4 also. The -1 over n-2 part, you can actually ignore it because it's just an alternating sequence. Ultimately, it's going to converge towards 0. And it's a little hard to take that derivative of -1 raised to n-2, but it's just alternating. So that's why I can sort of just push off to the side. Like, this is either -1 or 1. Like, it actually use a limit property. Like, you could just push that off to the side, let it be its own thing, and focus on n squared over n cubed plus 4, which I know n squared over n cubed plus 4 converges to 0. The other one's between -1 and 1, but you're multiplying 0 to it, so it just converges. So 4 is going to be a converge again. Yeah, no, go ahead. I got to take roll, by the way. Hold on. Yeah, go ahead. At the end, yes. Yeah, if ultimately you take the limit, that's what's happening. Yeah, everybody's out sick today. Okay. Not do that. Okay. Okay, for 5. Now in this case, you could ignore the 3 and kind of just focus on e to the 5n over negative e to the 2n. And if you do reduce the fraction or use properties of exponents, 5n minus 2n is 3n. So that's, the 3 becomes negligible, right? Or you could, if you want, you could do L'Hopital's rule if you want to do that. That would be 5 e to the 5n over negative 2 e to the 2n. But ultimately, you get -5/2 times what? Times e to the 3n. The -5/2 doesn't matter. If you plug in infinity, what are you going to get? negative infinity, right? So it's going to diverge. So it doesn't matter. 6, you have a radical going on here. You can actually square both top bottom separately if you want, or just push it off to the side and square it the whole limit because it's using the limit property. Of course, 2n over n plus 1 converges to 2 when n approaches infinity. We know this now. And you're square rooting it, so it's root 2, but it doesn't matter. That still converges. So for 7, also converging. 7 is that. So notice I broke off the exponents in that manner. And I focus on, and then 2 to the 2n becomes 4 to the n. And if I could push the 3/2 off to the side and focus on the limit of 3/4 raised to the n power. Now, what's happening here? 3/4 to the n power. What kind of sequence is that? Geometric. And it's a ratio between -1 and 1. It is. So it converges. It does. And actually, this eventually gets. Now, it's not the sum, by the way. We're not trying to do that. That's a different story. We'll do that today. This is more about just the last term. The last term converges to 0. It's just it's super small. So that will also converge. 8, you have a problem because if I try doing the squeeze theorem, and what I'll do is I'll compare it to n pi and negative n pi. To do that, because I know that what's the maximum cosine control, maximum value cosine value? 1, the lowest could be -1. I know that. So I know this is less than n pi and greater than negative n pi. Here's a problem, but what's n approaching? It's not 0, but it's if 0, then it would fully converge. Because that you squeeze them. But the problem is that that's negative then you're like, I don't know what to do with that. So it's not finite value. So even if I'm trying to squeeze theorem, that doesn't help me, right? So that's why just that diverges. For 9, of course, if you plug in infinity, now what's the natural log of infinity? It's still infinity, and 2 times infinity, natural log of that's still infinity. So what if I do L'Hopital's rule? What's the derivative ln over n? Sorry, what's the derivative ln n? And the derivative that's 1 over 2n, but in times its derivative is 2. So 1 over n, 2 over 2n. That was terrible. I fixed that. The 2's cancel. So you have 1 over n over 1 over n. What does that become? So that will converge. So the last term, remember, you're trying to find an infinite term. Will it converge? It will. If I use L'Hopital's rule, I could do that. So L'Hopital's rule is very powerful here. So I'll converge. What I do is I kind of did log. So, but this is not the only way you could do it, by the way. There are more algebraic techniques. And again, that's why I think Mr. York might be kind of upset that I'm teaching these guys this already, but play dumb next year. Like, I don't know this. And then you know it. Anyhow, I think what she was trying to get at with this homework she created was, can you guys get creative log properties? Of course you can get creative, right? You can make a natural log of 2 plus natural log of n. And if you think about it, for large n, that natural log 2 becomes negligible. So, or negligible, sorry, not negligible, but negligible, not fix my words. I need to ignore it. No, it has to be 1, so it converts still. So it's not significant. And the last for 15, sorry, for 10. Yeah, use squeeze theorem again. You know the range for sine n is -1 to 1. So definitely that expression sine n over root n could be less than 1 over root n or greater than -1 over root n. And if n's approaching infinity, well, 1 over root n is going towards 0. -1 over root n is also going towards 0. So this converges towards 0. So ultimately, the final term will be converging towards 0, or the infinite term. So what you're learning is you're starting to get a little bit familiar with how to apply limits to sequences and the whole concept of convergence divergence. That's kind of what was the intention of this lesson, this homework. So you guys are getting some exposure to that right now. Questions? We good? Okay. So we got new notes. The new notes are on that's geometry. So let's pull up the notes on impartial sums. So you guys have that already. Sorry, infinite partial sums, not impartial. I don't know what I call it. Infinite partial. Oh boy, I'm just mixing all my words today. All right, so let's pull this up here. Infinite partial sums. There we go. And see if I have a key for this. Might, hold on. Oh, I do. Let me download that here. One sec. Okay, let's get going, guys. Here we go. All right. So the basic idea of infinite series convergence, divergence is a sequence of partial sums. We call it partial sums because we're not looking at the whole sequence of terms, just a certain part of it, right? Um, so first, I'll determine if an infinite series converges or diverges by looking at the end behavior of the sequence of their partial sums. Okay, so we're going to break it down to their smaller sums. Formalize the first of 10 convergence divergence tests. Going about the other 9 AP Calculus B, C. Okay, so I think we're going to be talking about geometric today, which you guys are very familiar with. Anyhow, informal definition series. The focus on infinite series. While series can both be finite and infinite, our focus is studying infinite series. So simply put, a series of a list of numbers added up. As we know, 1, 2, 3, 4 is a sequence, but 1 plus 2 plus 3 plus 4 plus dot 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 is an infinite series because there are infinite number of terms that are being added together. We'll formally define what a series is once we understand what it means for a series to converge. But see if an infinite series converge or diverge, we must figure out a way to add up the infinite number of terms. So recall sigma notation. We know how it looks like. So for example, if you have a series of 1 squared plus 2 squared plus 3 squared plus dot dot dot, you write as sigma n equals 1 towards infinity of n squared. That's how we can condense the series. Now, the convergence divergence. When you add the terms of a finite series, you get a finite number. Duh, we know that. What happens if you add an infinite number of terms in an infinite series? So in order to get an idea of what happens when you add an infinite number of terms, you need to stop every so often and check the sum at the point. That's what we're calling a partial sum. So just you know what that means. So we stop to check, we call that a partial sum. So to become even more precise, you need to add one additional term at a time and then check the sum at each stopping point. So we'll use S sub n to represent a partial sum. So like S sub 4, S sub 5, that's how many terms you're adding up. When you add more and more terms of infinite series and the partial sums, your hope is that you approach a finite value, then the infinite series will converge. If it keeps getting bigger and bigger, of course, it diverges. Or if it oscillates between two numbers or different types of infinity, that also diverges. So those are the 3 things that could happen. So let's take a look at example 1. For each infinite series, find the first 4 partial sums, then write the partial sum as a sequence. So that's what you're doing. You're finding partial sums and then seeing if that has a pattern in itself, right? So in this case here, so what's the first term going to be here? Just what? Excuse me. Not just one. What's some of the first 2 terms? 3. What's some of the first 3 terms? What's some of the first 4 terms? 10. So I'm noticing if I write the partial sums as a sequence, how would it look? 1, 3, 6, 10, dot, dot, dot. So what's the pattern here? I mean, it's not arithmetic, right? Because it's not really geometric. The common difference is following an arithmetic sequence for sure, right? Um, so determine if possible the S sub n formula, the explicit formula for the partial sums in terms of n, if it's possible. So can I write this as a formula? We could try. I mean, it's not. Let's think about it. If it's possible, maybe we could. I don't know. What do you guys think? Anyone have an idea how I could write that explicitly? No ideas? Sorry, say again. N over 2. Oh, um, let's think about it. Does that make sense? You guys agree with Teddy? I don't know. I think it makes sense. Let's think about it. Because what's the first term? 1, right? And then we have n terms, but actually, no, that's to find each particular term. I don't know if that makes. Actually, does that make sense? Hold on, let me double check this.
Now, what do you talk about this thing?
So hold on a sec. Let's see here. Actually, no, you got it. That's right. You got it. Yeah, that makes sense. So yeah, you connect it to arithmetic. That's right. Yeah, you got it. Define each term. Right. We're not trying to find the sum. I think I'm overthinking this one. No, Ted's got it. Yeah, so that makes sense. Can you write? I guess what we want to say. Let me the explicit formula for each term. Yes, right. So you're 100% correct, Teddy. That is totally correct. We can use this to find each term in the sequence, right? So can this be used to find the fourth term? Sure. S4 is going to be that, right? So if I clean this up, what do you get? You get 1/2 n plus n squared over 2. So if I take the limit of that sequence, what's that limit going to be? Given it's just a parabola. Infinity, right. So this diverges. So what I did was just to understand what's happening. Because it's not very abstract. I computed partial sums for first term, second term, three term, fourth term, right? So 1, 2, 3, 10. I write down the sequence, and I try to come up with an explicit formula for the sequence of it. I know it's weird, but these sum values are now being part of the sequence. We're now getting away from the series into the sequence. And we're doing what we did in the previous unit. Try to come up with a formula for this sequence, which is this here. This makes sense because since each of these represent sum, you know this would be explicitly fine without these two terms here. And if I take a look at that expression as an approaching infinity, well, that's just the polynomial with n squared over 2 as a term. But yeah, of course it's infinity. So that diverges. So this series will diverge. I think it's pretty obvious when you see it, but to prove it, that's the proof you have to do. So that's the formality of writing it out. Okay, let's look at the next one. For part B. So let's do the first term. It's a little confusing because it starts at I'll write as this S0, S1, S2, S3. So obviously that's gonna be 1/3. What's next one gonna be? 1/3 plus. Wait, that's dumb. I'm sorry. It's 1. You're right. It's 1. Then 1 plus 1/3, which is what? 4/3. 1 plus 1/3 plus 1/9, which should be 4/3 plus 1/9, which should be 13/9. And this is 1 plus 1/3 plus 1/9 plus 1/27, which would be 13/9 plus 1/27, which should be 40/27. So if I list it out, you have 1. Actually, I'm gonna write it like this: 27 or 27. That's 1. 36 or 27. 39 over 27. And then 40 over. Okay. So ultimately, what do you think this is gonna? This will converge. Um, if you think about it, how would I find each particular term? What would I do? You guys see how this is a geometric sequence? What's your ratio? 1/3, right? So if you think about it, to write each explicit term, the first term is 1 already. We know this. But hold on a sec. I think we did. Or actually, let me back a little bit here. That makes sense. Yeah. Wait, no. Hold on. Something seems a little fishy here. If I did 1/3. Hold on. Let me pull up my thought notes on this stuff here. I had it. Okay. Yeah, I had it. Let me go back. Switch to red. So anyhow, the bottom becomes what? 2/3? Or 3/2? Yeah, that totally makes sense. Yeah, because if you plug in 0, you do get 1. You plug in 1, you get well, the first term, is 1. If you plug in 2, you get 8/9. Something seems a little off, but it's okay. But if I take the limit as n approaches infinity of S sub n, so this winds up just becoming a geometric sequence, right? So will this converge? Yeah, as n approaches infinity, what happens to this? So the sum gets closer and closer to, or the last term, sorry, the infinite term gets closer and closer to 3/2. So this will converge. So the answer is yes. Something seems a little off. Hold on. If I plug in 2, I get 1/9. That's 8/9 divided by 2/3. That'd be, yeah, if I have that. Right. Give me a sec. If you plug in 2, that's 8/9. That's 24/18. Oh, that does make sense. Yeah. It still reduces the same way. I'll lose my mind. Yeah, it makes sense. Yeah. It'll work. It'll be fine. Yeah. By what? Um, we'll talk about we'll talk about later because I can't remember how I assessed this last time, um, but you'll see when we get to some later stuff. Anyhow, let's keep moving, guys. Yeah. Well, it's just following a geometric sequence because this is a geometric formula. That's the sum of it. Sorry, that's the sum of a geometric series, right? The first term times 1 minus r raised to the n over 1 minus r, because every term here represents the sum, because each of these are sums of geometric series, right? So I'm just using this explicit formula of a geometric series to represent each term. Yeah, I was just getting confused because when I was plugging numbers in, because it started n equals 0, I was just getting myself twisted, but it makes sense. You will get each of these terms. Yeah, you can. Yeah, we're going to work towards that. Yeah. Okay, let's look at the next one here. Okay, so go and try the next. So you're going to do the same thing. Write out the first 4 partial sums. Determine the S sub n form and define an explicit form for each term in your new sequence. And then see if that sequence converges or diverges. I'll do it as well, and then we'll check in a few minutes. So go and try part C and D. Yeah, this one should be pretty straightforward.
Sounds like that's what it's like.
Nope. Nope. If you see an oscillation, you automatically go straight to diverge. You automatically conclude that. So for part C, oh, I thought I had frozen. Yeah, for part C, so we calculate the partial sums. N equals 1, the sum of the first term, of course, just -1. Some of the first two terms is 0. Some of the first three terms is back to -1. Some of the first four terms back to 0. So you write the partial sums as a sequence, -1, 0, -1, 0. That's never going to converge, right? That as a sequence is just going back and forth between two different numbers. Because there's an oscillating nature to it, you can automatically deduce that's one that diverge or that this will diverge. So you could just make that sense. You don't have to find S sub n. It's not necessary because that's why I say possible. It's not necessary. So, all right, let's go into part D. So notice I got a little creative here. We call this I think we call it partial fractions, where you break the fraction down to two smaller parts. So hopefully you guys can see that. And you can work on each one individually. The broken one's gonna be easy. You'll see why.
Waiting for it.
Okay, just to prime you for part D, notice I'm breaking off like this. Sigma n equals 1 to infinity of 3 over n plus 3. Sigma n equals 1 to infinity of 3 over n plus 4. So the first partial sum should be pretty, that's 3/4, right? The second partial sum will be 3/4 plus what? Plus 3/5, right? What will this be? 3/4 plus 3/5 plus what? 3/6. And the fourth partial sum would be what? Okay, do not find the LCD. You're going to drive yourself nuts. You'll totally drive yourself crazy. So don't do that. We'll do this for now. It's like a little pyramid we're making. Now for the blue. What's the first partial sum? 3/5, right? What's the second partial sum? What's the third partial sum? What's the fourth partial sum? Okay. What do we notice is happening here? Let's compare S4 for both series, right? So if I subtract what do you wind up getting? 3/4 plus 3/5 plus 3/6 plus 3/7 minus 3/5 minus 3/6 minus 3/7. So a whole bunch of things cancel. What cancels? What are you stuck with? So essentially that becomes 3/4 minus 3/8. Or if I write it as a formula, I could do this now. It's going to be 3/4 minus 3 over n plus 4. This is going to be your explicit formula to find each term in the sequence of partial sums. Right? 3/4 minus 3 over that. This is what I'm noticing is happening, right? As n approaches infinity, what happens to this term here? It goes away, right? It goes away. So if I take the limit as n approaches infinity of s sub n, that's 3/4 minus 0. You get 3/4. Does this converge? Yes, it does. So the series that we see there will converge. Again, it's not what term, it's all about a sum. So you have to be careful here. This is a sum, right? Not term. So we're adding things up now. So if you just had this expression here, a sub n equal this, of course we know that sequence converges. That's just 3 over infinity, which is 0. So of course I know the infinite term here is going to equal 0. But the sum, will the sum of this explicit formula of this formula, is that going to converge? The answer is yes. Because when I calculate the partial sums, I notice a pattern when I look at S4, like, oh, if I subtract the first S4 with the second S4, most terms cancel except for 3/4 minus 3/8. But in general, it's always going to be 3/4 minus 3 over n plus 4 in general. And if I take the limit as n approaches infinity of that expression, I do get 3/4, therefore this converges. So that will converge. And just kind of take a quick look here. Yep, that's what I noticed. Is happening for part D. So yeah, that will converge. Okay, let's keep on moving. Okay, so for on page 4 here. So infinite series and infinite sequence of partial sums. Okay, that's what it is. Infinite sequence of partial sums. So form definition, infinite series converge, diverge. Given a series, as you see there, let S sub n denotes nth partial sum. Fine, that's what we have. If the sequence S sub n is convergent, and limit as n approaches infinity, S sub n equals S some real number, then infinite series sigma a sub n is called convergent, and we write it as the following, and it's a sum. Otherwise, we diverge. So that's how we have to think of it. So now, as you can imagine, finding partial sums and trying to find n behavior of the partial sums determine convergence is quite tedious, and it's just that's terrible grammar. But it can be quite tedious, right? So once some of the terms of the sequence of partial sums are formed, it's not obvious at first whether the infinite series converges or diverges. So we have more efficient ways. There are different tests you'll learn in AP Calculus PC. The one that Ms. York is interested in have you guys see is for a geometric series. And that's pretty obvious. We know what's going to happen there. So if you have a pattern that follows this, geometry, what has to be true about R so that the sum of terms, the series, converges? What has to be true about R for the sum to converge? As you know, between A1 and 1, we know that. And in this case, for this particular example, sure. It does. Sorry, the one down below does. 1, 1/2, 1/4, 1/8, but 1 plus 1/2 plus 1/4. That's not a geometric series because we don't have a consistent ratio, obviously. So the test is this, right? If the ratio is bigger than 1, or the absolute value of the ratio is bigger than 1, it diverges. Otherwise, it will converge. And we know this already. We've done this many times. So, and I think in the notes she has it written like this, just to show you how it looks. Yeah. I mean, if we want to write this, you guys know what's happening here. So if ratio equals what itself, we do 1 to the n minus 1. That's a problem, right? Because you get these partial sums, either also just go on forever. So that's why r equals 1 is not okay. Because if you have 1, 2, 3, 4, 5 partial sums, that's really thick. Doesn't make sense. For r equals -1, it's oscillating, the partial sums oscillate, doesn't make sense either. You can't have absolute r equal to 1, it has to be less than 1. Or r equals -1 and 1. And we kind of worked this out like when we had the sum form of a geometric series of a times 1 minus r raised to the n power 1 minus r. If r is a number between -1 and 1, and you let n approach infinity, a portion of the numerator goes away, leaving just a over 1 minus r. But yeah, this one here is just showing you why the outside of r equals 1 is not okay. That won't converge. That will diverge. So we'll do a couple more and you guys can start homework. You already have the homework copy already handed out to you guys. So let's go to example 2. Oh, hold on. So here's how we'll approach these problems. So let's first figure out the first term. One, right? And what's the ratio? Series converges. So my sum will be this. So you get 5/2. That's pretty obvious. Let's take a look at the next one. What will your first term be for this one here? Four, right? Okay, good. Now, if we think about it, if I rewrite this, you can think of it like this: 2 to the k squared. Actually, does that make sense? Hold on. Let me do this first. No, I'll do that. I was right in doing that. Or actually, that makes sense, right? Yeah, because you do k plus k, which is 2k. Okay, so we're okay with that so far? All right. So if I do this, or actually, I was right in doing this initially. Sorry about that. I keep changing my mind. You agree with that?
Mhm.
And then you agree with this. And then you would agree that this is 4/3. Now, what's my R value here? What was it? Sorry? 4/3. So this will diverge. But you have to prove it. Because your ratio is bigger than 1. So just get a little creative with the way you treat the exponents. Okay, we're good. All right, so yeah, I'm pretty sure the answer key shows that as well. Yep, our R is 4/3. Okay, so homework will be this. You guys actually have about 12-ish minutes. Put attention if you like. If you have VPs to study for, it's totally fine. I get it. Some of you guys have Gov or stats or other stuff. Yeah, so you got this stuff here. And switch keys included in your homework packets. So yeah, just have at it.